Download this code from codegive.com, link in the description below. OK, let's dive deep into Malloc and memory management in C, transforming you from a novice to a more confident and competent memory manager. This will be a comprehensive guide covering concepts, best practices, potential pitfalls, and code examples. Table of Contents *. 1. Fundamentals, understanding Malloc, calloc, realloc, and free. 2. How Malloc works, simplified view. 3. Basic usage and common patterns. 4. Error handling and memory allocation failures. 5. Memory leaks, detection and prevention. 6. Double free and heap corruption. 7. Realloc in detail, resizing memory blocks. 8. Calloc vs Malloc, zero initialization. 9. Advanced techniques and best practices *. Memory pools. Custom allocators. Alignment considerations. 10 Tools for memory debugging and analysis *. Val grind. Address sanitizer, ASAN. 11 Code examples, a practical demonstration. 12 Alternatives to Malloc, if you're curious. 13 Conclusion, mastering dynamic memory management. 1. Fundamentals, understanding Malloc, calloc, realloc, and free. In C, dynamic memory allocation allows you to request memory during program execution, as opposed to having all memory allocated at compile time. The functions that enable this are *malloc, size_t size, *allocate memory. It allocates a block of memory of the specified size, in bytes. It returns a pointer to the beginning of the allocated block. Crucially, the memory is uninitialized, its contents are undefined, it could contain garbage. If allocation fails, example not enough memory, it returns null. *calloc, size_t number, size_t size, *allocate and clear memory. It allocates a block of memory for an array of number elements, each of size bytes. Importantly, it initializes all bytes of the allocated memory to 0. Returns a pointer to the allocated memory, or null on failure. *realloc, void ptr, size_t size, reallocate memory. It attempts to resize a previously allocated block of memory pointed to by ptr to the new size. It can expand the existing block in place, if there's enough contiguous space. Allocate a new block of memory, copy the contents of the old block to the new block, and free the old block. Return null if it fails to allocate the new block. If ptr is null, realloc behaves like malloc, size. If size is 0 and ptr is not null, realloc frees the block pointed to by ptr and returns null. Free, void ptr, deallocate memory. It releases the memory block pointed to by ptr, making it available for future allocations. Important *ptr must be a pointer returned by a previous call to malloc, calloc, or realloc. Passing an invalid pointer to free, example a pointer to the stack or a pointer that has already been freed, results in undefined behavior, often leading to crashes or heap corruption. 2. How Malloc works, simplified view. Malloc, and the other allocation functions, interacts with the operating system's memory management system. Here's a very simplified, high-level overview. 1. Heap Malloc operates on a region of memory called the heap. The heap is a large, contiguous area of memory that the program can dynamically request and release. 2. Memory management *. The C runtime library, example glibc on Linux, MSVCRT on Windows, provides an implementation of Malloc. This implementation manages the heap, keeping track of which blocks are allocated and which are free. 3. Block metadata * when you call malloc, the malloc implementation allocates a block of memory from the heap. It also adds some metadata before the start of the returned memory block. This metadata usually includes * the size of the allocated block, * flags indicating whether the block is free or allocated, * pointers to adjacent free blocks, in some implementations. 4. Splitting and coalescing *. When malloc needs to allocate memory, it searches for a free block that is large enough. If it finds a block that is larger than the requested size, it splits the block into two, one allocated block of the requested size and one smaller free block. * When free is called, the malloc implementation marks the block as free. It may also coalesce adjacent free blocks into a single, larger free block to reduce fragmentation. 5. Operating system interaction *. If the malloc implementation runs out of memory in the heap, it can request more memory from the operating system using system calls like sbrk, on Unix-like systems, or virtualalloc, on Windows. Important note *. The actual implementation of malloc can be quite complex and varies between different C runtime libraries. The details above are a simplified explanation to help you understand the basic concepts. 3. Basic usage and common patterns. Here's how you typically use malloc to allocate memory for different data types. Key points *. Asterisk includes stlib.h*. This header file declares malloc, calloc, realloc, and free. Size of operator * always use size of to determine the size of the data type you are allocating memory for. This makes your code more portable, because the size of data types can vary between different architectures, and easier to maintain. Casting in C, it's good practice to cast the return value of malloc to the appropriate pointer type, example int *, float *. This isn't strictly required in C, it's implicit, but it improves code clarity and can help catch errors. Error checking * always check if malloc, or calloc or realloc, returns null. If it does, it means the allocation failed, and you need to handle the error gracefully, example print an error message and exit the program. Free * it is essential to free the memory you allocate using malloc, or calloc or realloc, when you are finished with it. Failing to do so results in a memory leak. 4. Error handling and memory allocation failures. As seen in the previous example, it's crucial to check for null after calling malloc, calloc, or realloc. Here's how you can handle memory allocation failures. Explanation *. Per the per function is a useful way to print an error message to str that includes the system error message associated with the last error that occurred. In this case, it will likely print something like malloc failed, cannot allocate memory. Exit with an error code * returning a non-zero value from main, signals to the operating system that the program terminated with an error. This is useful for scripting and automation. Error messages * provide informative error messages to help the user understand why the program failed. 5. Memory leaks, detection and prevention. A memory leak occurs when you allocate memory using malloc, or calloc or realloc, but fail to free it when you are finished with it. Over time, memory leaks can consume all available memory, causing your program to slow down or crash. Causes of memory leaks *. Forgetting to free * the most common cause. Losing the pointer to the allocated memory *. If you overwrite the pointer that holds the address of the allocated memory, you can no longer free it. Asterisk exceptions or early returns. Asterisk if an exception is thrown or the function returns before free is called, the memory will be leaked. Preventing memory leaks. Asterisk. Asterisk always free what you malloc. Asterisk this is the golden rule. Asterisk use a consistent allocation/deallocation pattern. Asterisk for example, if you allocate memory in a function, make sure that the corresponding free call happens within the same function or in its caller. Asterisk keep track of allocated memory. Asterisk for complex applications, you might want to use data structures, example linked lists, to keep track of all allocated memory and ensure that it is all freed before the program exits. Asterisk use smart pointers. In C++, if you are using C++, smart pointers like std_unique_ptr and std_shared_ptr can automatically manage memory and prevent leaks. C doesn't have smart pointers natively, but you can implement similar concepts. Example of a memory leak. Asterisk 6. Double free and heap corruption. Calling free on the same memory block twice is a serious error called a double free dot. It leads to heap corruption, which can cause unpredictable behavior, crashes, and security vulnerabilities. Why is double free bad? When you free a memory block, the malloc implementation marks it as free and may add it to a list of available blocks. If you free the same block again, the malloc implementation might try to manipulate the metadata of that block, which has already been marked as free or has been reallocated to someone else. This can corrupt the internal data structures used by malloc to manage the heap. Example of double free. Asterisk. Preventing double free and heap corruption. Asterisk. Asterisk careful programming. Asterisk the best way to prevent double free errors is to be extremely careful when writing your code. Make sure that you only free a memory block once, and that you don't accidentally free the same block multiple times. Asterisk set pointers to null after free. Asterisk after you free a memory block, set the pointer to null. This can help you detect double free errors, because free, null, is safe, it does nothing. Asterisk use a debugger. Asterisk if you suspect that you have a double free error, use a debugger to step through your code and see exactly when the error occurs. Asterisk memory debugging tools, valgrind, ASAN tools like valgrind and address sanitizer can automatically detect double free errors and heap corruption. We'll discuss these later. 7. Realloc in detail, resizing memory blocks. Realloc is used to change the size of a previously allocated memory block. How realloc works. Asterisk 1. Realloc, PTR, size, asterisk. Asterisk if PTR is null, realloc behaves like malloc, size. Asterisk if size is 0 and PTR is not null, realloc frees the block pointed to by PTR and returns null. Asterisk otherwise, realloc tries to resize the block pointed to by PTR to the new size. 2. Resizing in place. Asterisk if there is enough contiguous free space after the existing block, realloc can simply expand the block in place. In this case, realloc returns the same pointer PTR. 3. Allocating a new block. Asterisk if there is not enough contiguous free space after the existing block, realloc will asterisk allocate a new block of memory of the requested size. Asterisk copy the contents of the old block to the new block, up to the minimum of the old size and the new size. Asterisk free the old block. Asterisk return a pointer to the new block. 4. Failure. Asterisk if realloc cannot allocate the new block, it returns null. Important. Asterisk in this case, the original block pointed to by PTR is still valid and must be freed eventually. Example of realloc. Asterisk. Important considerations when using realloc. Asterisk. Asterisk error handling. Asterisk always check if realloc returns null. If it does, the original memory block is still valid and must be freed. If you don't free it, you'll leak memory. Preserving data realloc will copy the contents of the old block to the new block, up to the minimum of the old size and the new size. Make sure that you copy any data you need before freeing the old block, if realloc returns a new pointer. Memory movement realloc may move the memory block to a new location. This means that any pointers to the original memory block will become invalid after realloc. You need to update those pointers to point to the new location. Efficiency realloc can be an expensive operation, especially if it needs to allocate a new block and copy the data. If you know in advance how much memory you need, it's often more efficient to allocate the memory once using malloc or calloc. Do not directly assign the return of realloc to the original pointer before checking for null. If realloc fails, the original pointer will be lost. 8. Calloc vs malloc, zero initialization. Both malloc and calloc allocate memory, but there's a crucial difference. Malloc allocates memory, but the contents are uninitialized. You get whatever garbage was previously in that memory location. Calloc allocates memory and initializes all bytes to 0. When to use calloc when you need 0 initialized memory this is useful for initializing data structures, arrays of numbers, or any data that needs to start with a known value. For security zeroing out memory can help prevent information leaks, especially when dealing with sensitive data. Example of calloc Performance considerations calloc is generally slightly slower than malloc because it has to zero out the memory. If you don't need 0 initialized memory, malloc is usually a better choice. If you need 0 initialized memory but want the performance of malloc, you can allocate using malloc, then use memz to clear the memory. 9. Advanced techniques and best practices. Now let's move beyond the basics and explore some advanced techniques and best practices for memory management. Memory pools A memory pool, also called a memory arena or a fixed size allocator, is a technique for improving the efficiency of memory allocation and deallocation in situations where you need to allocate and deallocate many small, fixed-size objects. Instead of using malloc and free directly for each object, you allocate a large block of memory from which you then allocate smaller blocks. Benefits of memory pools faster allocation / deallocation allocating from a pre-allocated pool is generally much faster than calling malloc and free for each object. Reduced fragmentation memory pools can help reduce memory fragmentation, which can improve performance. Deterministic behavior memory pools provide more predictable and deterministic allocation behavior. Simplified management easier to track allocated and deallocated blocks within the pool. Example of a simple memory pool, conceptual. Limitations of simple memory pools fixed block size the blocks in a memory pool are usually of a fixed size. This can lead to wasted memory if you need to allocate objects of different sizes. No true free in the simplest form, you don't individually free blocks within the pool until you destroy the entire pool. More sophisticated implementations might maintain a linked list of free blocks for reuse. Not suitable for all situations. Memory pools are most effective when you have many small, fixed-size objects that need to be allocated and deallocated frequently. They are not a good choice for allocating large, variable-size objects. Custom allocators. A custom allocator allows you to create your own memory allocation functions that can be tailored to the specific needs of your application. This can improve performance, reduce fragmentation, and provide more control over memory management. Reasons to use a custom allocator asterisk. Asterisk performance optimization asterisk you can optimize the allocator for the specific allocation patterns of your application. Asterisk fragmentation control asterisk you can design the allocator to minimize memory fragmentation. Asterisk memory tracking and debugging asterisk you can add memory tracking and debugging features to the allocator. Asterisk portability asterisk you can create a custom allocator that is portable across different platforms. Example of a very basic custom allocator asterisk. Important considerations for custom allocators asterisk. Asterisk fragmentation asterisk you need to carefully consider how to manage free blocks within the allocator to minimize fragmentation. Asterisk thread safety asterisk if the allocator will be used in a multi-threaded environment, you need to ensure that it is thread safe. This typically involves using locks or other synchronization mechanisms. Asterisk complexity asterisk custom allocators can be complex to implement and debug. Only use them if you have a clear understanding of the performance benefits and the trade-offs involved. Asterisk debugging asterisk ensure you have thorough debugging and error checking mechanisms in place. Asterisk alignment considerations. Memory alignment refers to the requirement that data of certain types must be stored at memory addresses that are multiples of a certain value, the alignment. This is often dictated by the processor architecture to improve performance. Misaligned memory access can lead to slower performance, and in some cases, can cause program crashes, especially on certain architectures like some ARM processors. Why alignment matters asterisk. Asterisk performance asterisk modern processors often retrieve data from memory in chunks, example 4 bytes, 8 bytes, or 16 bytes. If a data item is not aligned to the appropriate boundary, the processor might need to perform multiple memory accesses to retrieve the data, which is slower. Asterisk portability asterisk alignment requirements can vary between different architectures. If you don't consider alignment, your code might work on one architecture but crash on another. Alignment of data types asterisk. The alignment requirements for data types are typically as follows. Asterisk char, alignment of 1 byte. Asterisk short, alignment of 2 bytes. Asterisk int, alignment of 4 bytes. Asterisk long, alignment of 4 bytes, on 32-bit systems, or 8 bytes, on 64-bit systems. Asterisk long, alignment of 8 bytes. Asterisk float, alignment of 4 bytes. Asterisk double, alignment of 8 bytes. Asterisk pointers, alignment of 4 bytes, on 32-bit systems, or 8 bytes, on 64-bit systems. Asterisk structures, alignment is usually determined by the largest alignment requirement of its members. How Malloc handles alignment asterisk. The malloc function is typically implemented to return memory addresses that are aligned to the most stringent alignment requirement of the target architecture. On most systems, malloc returns memory that is aligned to at least 8 bytes or 16 bytes. This ensures that you can safely store any data type in the allocated memory without violating alignment requirements. Example demonstrating potential alignment issues with structures asterisk. Notes about alignment asterisk. Asterisk compiler padding asterisk compilers often insert padding bytes into structures to ensure that the members are properly aligned. The pragma pack directive, or its equivalent on other compilers, can control structure packing, but should be used carefully, as it can degrade performance if it causes misaligned memory access. Asterisk underscore aligness keyword. C11 introduced the underscore aligness keyword, which allows you to specify the alignment requirement for a variable or a structure member. Asterisk aligned underscore alloc, C11 also introduced the aligned_alloc function, which allows you to allocate memory with a specific alignment. However, aligned_alloc is not widely supported and its behavior can vary between implementations. Memory pool alignment. When creating custom memory pools, it's important to ensure that the pool is aligned to a suitable boundary and that the blocks allocated from the pool are also properly aligned. 10. Tools for memory debugging and analysis. Memory errors can be notoriously difficult to debug. Fortunately, there are tools that can help you detect and diagnose memory leaks, double free errors, heap corruption, and other memory-related problems. Valgrind. Valgrind is a powerful and versatile memory debugging and profiling tool suite for Linux and other Unix-like systems. It includes several tools, but the most commonly used for memory debugging is MEMC-HEC. MEMC-HEC detects a wide range of memory errors, including memory leaks. Detects memory that has been allocated but not freed. Invalid reads and writes. Detects reads and writes to memory that has not been allocated or that has been freed. Use of uninitialized memory. Detects cases where you are using the value of a variable before it has been initialized. Double free errors. Detects attempts to free the same memory block twice. Overlapping source and destination addresses. Detects cases where the source and destination addresses in a memp or memov operation overlap. How to use Valgrind, MEMC-HEC. 1. Compile your program with debugging information. Use the G flag when compiling your C code. This includes debugging information in the executable, which makes Valgrind's reports more informative. 2. Run your program under Valgrind *. 3. Analyze the Valgrind output *. Valgrind will print detailed reports of any memory errors that it detects. The reports will include the type of error, the address of the memory involved, and the line of code where the error occurred. Example: Valgrind output *= == 1 2 3 4 5 == MEMC-HEC, a memory error detector. == 1 2 3 4 5